All right, so I wanted to just finish up the one last example of a skill that we'll need moving forward from a skill from Chapter 2. So where we were when we finished up class was we were talking about the dot product. And the dot product between two vectors, A and B, can be found by taking the magnitude of the two vectors multiplied by the cosine of the angle between them. And what I had pointed out at the end of class is if we think about taking the projection of vector A onto vector B, we get a length of a vector which is equal to A times the cosine of theta. So this is the projection of A onto B. What does that mean? It means that that is the portion of vector A that is parallel to vector B. And that's just sort of something to understand when we talk about the dot product, and it is related to the problem that I wanted to cover. So in this problem right here, we have a vector F that has a magnitude of 500 newtons. And the question says, can you find the magnitude of the projection of the force F along the AA axis? So the blue line represents the AA axis. It's a line that joins 2 points in the three-dimensional Cartesian space. The first thing, and what we want to do is we want to project F onto that, which is actually going to be done by taking vector F and dotting it with the unit vector that is along that blue line. And I'm just going to call that unit vector AA because that's the name of the line. This is going to be your answer to the question they want you to do. Now, we have a little bit of work to do before we're ready to figure that out. The first thing we need to do is we need to write the vector F. Now, the vector F has a y and a z component. It's only in that plane. It does not have an x component. And I wanted to point out this little triangle right here because this is another way that the orientation of a vector can be given to you as opposed to given an angle relative to an axis. Basically what it's saying is the components of vector F have the ratio of this 3, 4, 5 triangle. That is, the side 3 would be proportional to the z component, and the 4 side would be proportional to the y component. And what we could do is we could sort of imagine that if this was the little angle right in here, theta, we could say that we would find, for instance, the y component would be given by f times the cosine of that angle, but the cosine of that angle can be given by the ratio of the sides of that triangle, which would be the adjacent side, which is 4, over the hypotenuse, which is 5. So for instance, so we would say this is Fy times the j plus Fz times the k. The y component is going to be given by the magnitude of the vector times the cosine of the angle, which would be given by the ratio 4/5. And so this is something else that we're going to have to be doing as we go through our problems. Sometimes we won't be given the angle, but we'll be given these little triangles, and we can just use the sides of those triangles to express their ratios as they would give the sine or the cosine of the angle, whatever we desire. We shouldn't use those sides to figure out what the angle is because that would be extra work. Now, the z component is going to be given by the sine of that angle, which can be written as 3/5. And I should also note that the y component for this one is negative. So this ends up to be, so we would take 500, the negative sign, times 4/5, j hat, and then the 500 times 3/5 times k hat. And so our vector F can be written as minus 400j plus 300. Okay. So that's how we would write vector vector F. Now, the way that we would write the the unit vector, the first thing I'm going to do is I'm going to find the position vector that goes from A to A. And so it's connecting 2 points. This point has coordinates of 0, 0, 0 because it's at the origin of the coordinate system. And then I'm going to use this point right here because they're giving us some information about that. And this is where we have to be careful. If I look at the picture, I can see that this point is 1 meter in the negative x direction, so this is -1. And it's 2 meters in the y direction, so that's 2. And it's 2 meters in the z direction. Oops, sorry. 2, sorry. So those are the coordinates, and I'm going to use those to figure out the position vector that goes from here to here. And so I'm going to take these coordinates here and subtract these. So I get -1 minus 0 for my x component. I get 2 minus 0 for my y component. And I get 2 minus 0 for my z component. So this is going to be minus I plus 2j plus 2k. Now the magnitude of that is going to be found by taking the square of these components, adding them together. And so that is going to be the square root of 9, which is 3. And so the unit vector in that direction would be found by taking the vector I just found and dividing it by 3. So I get -1/3 plus 2/3 j plus 2/3 k. All right, and so then square root, oops. So what I had my force vector was -400 j plus 300 k, and my unit vector that points along that blue line is -1/3 I plus 2/3 j plus 2/3 k. And what I want to do is I want to answer the question, to find the magnitude of the projection of the force F along that line, I would take the dot product of that force with a unit vector that is parallel to the line. Now, by using the unit vector, we're not affecting the magnitude of the component of force that I'm looking for, because that just has a magnitude of 1. And so we're going to take the -400 j plus 300 k dotted with a -1/3 I plus 2/3 j plus 2/3 k. And now we already talked about how we find the dot product for two vectors written in unit vector form. So I get -400 times 2/3, and then 300 times 2/3. And this answer, you can see, is going to give me a negative number, and so when I present the answer, since they ask for the magnitude, I'm going to just figure out the I'm just going to figure out what the magnitude of that answer is. And so I have, so this is going to be -266.7, and then plus 200. So it would be -66.7, but I want the magnitude, and so I just write it 66.7 newtons. All right, and so that's how I use the dot product to answer a question like this. There are a couple of problems where we have to sort of figure out how a vector might project onto a line that's not an x or y or z axis, and we can use this kind of approach to do that.